Hello, today we will discuss about the tractive effort required for the propulsion of train, mechanics of train and coefficient of adhesion. Now here, to find out the total tractive effort required for the propulsion of the train, we'll find that first we have to find out the tractive effort required for acceleration. Now here, the basic formula for the force is given as mass into acceleration. Now mass, because W is the dead weight of the train in tons, we multiply it by 1000. So 1000 into W will be in kg multiplied by, you are considering the acceleration here, that is alpha into 1000 divided by 3600. So here you get acceleration as 0.2778 alpha. So I put down here the tractive effort required is equal to, for acceleration, is equal to 277.8 W into alpha. But here when you consider the tractive effort, it's only the linear acceleration that we are considering. But if we have to consider the rotational acceleration also, then instead of dead weight we have to consider another weight that is called as accelerating weight. And accelerating weight is denoted by W suffix E. Accelerating weight is always greater than the dead weight, because when you're considering the accelerating weight, you are taking into consideration the effect of rotational inertia. So if I consider here now, instead of dead weight, if I consider accelerating weight, then my tractive effort required for acceleration works out to be 277.8 W suffix C alpha newtons, where W suffix C is accelerating weight and alpha is the acceleration. In this case, it is in kilometers per hour per second. Now to work out the tractive effort for overcoming the effect of gravity, it is given as the Fg is equal to 1000 into W sine theta kg. So here if you consider W as the dead weight of the train, then this dead weight of the train can be resolved into two components. One is the W sine theta and one is the W cos theta. Now W sine theta is the component basically which is responsible for, which opposes the motion of the train in the up direction here. So that is why we consider here, I consider the W sine theta component. So the tractive effort required to overcome the effect of gravity is equal to 1000 into W sine theta. Next slide. When I move to the next slide, you'll find that in railways, the gradient is always expressed as a rise in meters in a track over a distance of 100 meters, and is denoted by the percentage gradient, that is G, which is equal to, is given as sine theta into 100, or in other words I can say that sine theta is equal to G upon 100. So this G is the percentage gradient. So I can say that the tractive effort required to overcome the effect of gravity is equal to 1000 into W, and sine theta is taken as G upon 100, or this 0 and this 0 gets cancelled out here. So I can say the tractive effort required to overcome the effect of gravity is 10 into W into G kilograms. But I want to get this tractive effort required to overcome the effect of gravity in newtons. So I multiply it by 9.81. So when I do that, finally I get the equation as tractive effort required to overcome the effect of gravity is equal to 10 into 9.81, that is 98.1 Wg, where W is the dead weight of the train and G is the percentage gradient, which is generally given in this way, sine theta into 100. Last thing that we have to find out is the tractive effort required for overcoming the train resistance. The train resistance basically consists of all the forces resisting the motion of a train when it is running at uniform speed as a straight and level track. Now the train resistance is given as equal to K1 plus K2V plus K3V square, where K1, K2, K3 are constants depending upon the train and the type of track, and V there is the speed in kilometers per hour. The first two terms, that is K1 plus K2V, they represent the mechanical resistance here, while the last term, that is K3V square, it represents the air resistance. Now the tractive effort required to overcome the train resistance is given as W, that is dead weight of the train, multiplied by R, small r, newtons, where small r is called as the specific resistance of the train in newtons per ton, and it is newtons per ton of the dead weight. So the tractive effort now, the total tractive effort, then I can say is equal to the tractive effort required for acceleration plus minus tractive effort required to overcome the effect of gravity plus the tractive effort required to overcome the train resistance. Now here plus sign I consider if the train is moving up the gradient, and minus sign I use if the train is moving down the gradient. So putting down all the values of FA, FG and FR, I will say that tractive effort, total tractive effort required then is equal to 277.8 WE alpha plus or minus 98.1 WG plus W into small r. Similarly, the power output of from the driving axles P can be given by this equation, that is tractive effort multiplied by this V is the speed in kilometers per hour multiplied by 1000 upon 3600. This will give you in watts. And if you simply consider the power output from the driving axles P is equal to Ft, the tractive effort multiplied by the speed in kilometers per hour divided by 3600, you will get the power output in kilowatts, where we can see is the speed in kilometers per hour. Now this equation for the tractive effort, I can slightly modify it and use it to find out the coasting retardation, that is minus beta c. So during the coasting, when you consider a quadrilateral speed time curve for the suburban services, when the coasting is on, that time the supply to the electrical motors is switched off. So tractive effort automatically is becoming equal to 0. So when I put that tractive effort equal to 0 during coasting, the speed is reducing. So in the first term here, instead of alpha, there will be minus beta c, where beta c is the coasting retardation and it's taken minus because during coasting the speed goes on reducing. So this becomes a modified equation which you can use to find out beta c, that is the coasting retardation. For that you have to put Ft equal to 0, and my equation then becomes 277.8 We into bracket minus beta c plus or minus 98.1 Wg plus Wr. I have tried to solve the problem here on the, you can see is the quadrilateral speed time curve. So in this numerical, if you will go through the numerical, you will find that the time required for acceleration is given as 24 seconds, time required for coasting is given as 69 seconds, time required for braking is given as 11 seconds. The V1, the speed at the end of acceleration, this one is given as 48 kilometers per hour. So using the standard equations for the quadrilateral speed time curve, you will find that T1 is equal to V1 upon alpha. So I can say from here this equation I can get alpha, that is acceleration, V1 upon T1, that is 48 upon 224, which works out to be 2 kilometers per hour per second. Similarly, if I use this equation, tractive effort equation, to find out minus beta c or beta c, I have to put Ft equal to 0. Now the accelerating weight is equal to 1.1 into W here, because you can see in the numerical as it's given that you have to consider 10% as rotational inertia. So if I consider 10% as rotational inertia, then the accelerating weight We becomes equal to 1.1 into W. So putting down all the values in this equation here, tractive effort equal to 0, so minus 277.8 into 1.1 into W beta c plus. Now there is nothing given here in this numerical whether the train is moving up the gradient or down the gradient. So we are assuming here that the train is moving on a level track. So if the train is moving on the level track, G will be considered as 0. So the second term will vanish out. We can see here, considering level track, G is 0. So the second term is vanishing out, plus dead weight of the train, W, multiplied by specific resistance of the train is given in the numerical as 58 newtons per ton, we can see. So putting down all these values, WW gets cancelled out here. And from this equation, you can find out beta C. It works out to be 0.19 kilometers per hour per second. Now, to find out the total distance of the run for a quadrilateral speed time curve, with reference to this curve, we find this is the equation. This V1 into T1 upon 7200. That is, this part is the distance traveled by the train during acceleration. Then plus V1 plus V2 upon 2 into T2 by 3600. This is the second term, is the distance traveled by the train during coasting, plus V2 T3 upon 7200. This is the last term, is the distance traveled by the train during braking. So putting down all the values, V1 is 48 kilometers per hour, that is given. T1 24 seconds, it is given. Then V1 plus V2, that is 48 plus 34.9. V2 we are finding out from here. That is by using this equation, T2 is equal to V1 minus V2 upon beta C. T2 is given 69, which is equal to V1 is given 48 minus V2 is not known, divided by beta C we have found out from here, that is 0.19. So putting down all the values here, we get V2 34.9 kilometers per hour, which is nothing but, you can see the speed of the train at the end of the coasting. So putting down these values here, V1 plus V2, then T2 is 69, which is given 69 seconds in the numerical, plus again V2 34.9 into T3 is given as 11 seconds divided by 7200. You'll find that the total distance of the run is working out to be 1 kilometer. Scheduled time then for the train is equal to the time required for acceleration plus time required for coasting plus time required for the braking plus the stop time. So adding all these things, stop time is given in the numerical as 20 seconds. So scheduled time becomes 124 seconds. So the scheduled speed then is given by the formula distance traveled by the train during the run multiplied by 3600 divided by the scheduled time. Distance traveled during the run is worked out here as 1 kilometer, so it is taken as 1 into 3600 constant divided by scheduled time is 124 seconds. So when you do the calculations, you'll find the scheduled speed of the train is working out to be around 29 kilometers per hour. So this is a numerical where our ultimate aim is to find out the scheduled speed. To find out the scheduled speed, first we are finding out the distance traveled by the train during the run, then you are finding out the scheduled time, and for finding out this S, distance traveled during the run, you require V2. So you find out the V2 here. To find out V2, I require beta C. So I'm finding out beta C from this equation. So all these things are nice numerical where you are asked to find out the scheduled speed of the train. Next we move on to the mechanics of the train here. So you'll find that the armature of the driving motor has a pinion of diameter small d. Has a pinion of diameter d dash. So you can see it's a pinion that is shown whose diameter is d dash attached to it. The pinion transfers its motion to the gear wheel. The tractive effort at the edge of the pinion is transferred to the driving wheel by means of a gear wheel. Let the torque developed by the motor be capital T Newton meters. Then tractive effort at the edge of the pinion is given by the equation. This is the torque developed, that is equal to F dash, the tractive effort, into D dash by 2, where D dash is the diameter of the motor pinion. Or in other words, I can say that the tractive effort F dash at the edge of the pinion is given as equal to 2 into torque developed by the motor in Newton meters divided by D dash, that is the diameter of the motor pinion. Tractive effort transferred to the driving wheel is given as eta into F dash, that is this F dash, into small d by capital D, where small d, it's given here, small d is the diameter of the gear wheel in meters and capital D is the diameter of the driving wheel. So small d you can see is the diameter of the gear wheel and capital D is the diameter of the driving wheel. So the tractive effort transferred to the driving wheel, F is given as eta into F dash into bracket small d upon capital D, where eta is the efficiency of transmission and small d upon D dash is called as gamma, the gear ratio. So putting down all the values here, F then tractive effort transferred to the driving wheel is equal to eta into 2t upon D dash. So I'm putting this value of F dash here into bracket small d upon capital D. Or in other words, I can write down the final equation as the tractive effort transferred to the driving wheel, eta, is equal to eta, the efficiency of transmission, T, the torque developed by the motor in Newton meter, then 2 into gamma, the gear ratio, divided by capital D, that is the diameter of the driving wheel. Now, looking at all the other terms kept as constant, you'll find that the tractive effort which is transferred to the driving wheel from this equation, we can see is directly proportional to the torque. So here we can conclude that, as we go on increasing the torque exerted by the traction motor, I can go on increasing the tractive effort. But you'll find that there will be a certain limit up to which you can increase the tractive effort exerted by the traction motors. Because if you just go on increasing the torque exerted by the traction motors just to increase the tractive effort, a stage will come where you'll find that any further increase in the torque exerted by the motor, instead of increasing the tractive effort, you'll find that it will cause the slipping of the wheels from the track rails. So that is very important. So Here then we introduce one term which is called as the coefficient of adhesion. So if I call the coefficient adhesion as mu, which is, then I can say, is equal to the tractive effort that is required just to slip the wheels from the track divided by the adhesive weight. Now we know that we have three types of weight now. So dead weight of the train we have seen, the accelerating weight we know the accelerating weight is always greater than the dead weight, because when you're considering the accelerating weight, you are considering the effect of the rotational inertia. What is the adhesive weight? Adhesive weight, we can define it as the adhesive weight is the weight that is available at the driving wheels of the locomotive and which is responsible for the frictional grip between the driving wheels of the locomotive and the track rails. So coefficient, whenever you are considering the coefficient of adhesion, you will find that we always consider the adhesive weight. So it's a ratio of tractive effort required just to slip the wheels from the track rails divided by the adhesive weight. Now what are the factors on which this coefficient of adhesion depends? Now you'll find that if there are the imperfections in the track or unevenness in the track surfaces, it will reduce the coefficient of adhesion. Similarly, presence of oil, dew, etc. on the track reduces coefficient of adhesion. Presence of rust, sand, dust or dry rails improves coefficient of adhesion, that is mu. Loss of adhesion generally takes place in the morning hours. Normal value of coefficient of adhesion with clean dry rails is around 0.25 and with wet or greasy rails is as low as around 0.08. So these are the minimum, the maximum values of the coefficient of adhesion. Now coefficient of adhesion is basically also influenced by the mechanical parts, because if you try to, there is a sudden increase of tractive effort, it will affect the coefficient of adhesion. If you suddenly try to increase the tractive effort, or if you suddenly try to decrease the tractive effort, then you will find that the chances or probability of the driving wheels slipping off the rail tracks becomes more. Similarly, greater the moment of inertia of the revolving mass is, greater will be the coefficient of adhesion and less will be the slip. Coefficient of adhesion reduces with increase in speed. So as you increase the speed, coefficient of adhesion reduces. Coefficient of adhesion is greater in electric traction as compared to that in steam traction, because in steam traction we have seen that the steam engine drive, the center of gravity and the center of gravity in case of steam engine drive and the center of gravity in case of electric traction, there's a difference. So in steam engine drive the center of gravity is high because the presence of the boiler and all those heavy equipments is there, as compared to that in the electric traction you'll find that the center of gravity is low. So because of that, you'll find that the coefficient of adhesion is greater in electric traction as compared to that in the steam traction. Also in electric traction, you'll find that the torque exerted is continuous. So that is why also you'll find that the coefficient of adhesion is better in electric traction as compared to the steam traction or steam engine drive, where the torque is not continuous. The torque exerted is pulsating, which causes jolting and skidding, and because of all this, because the torque is pulsating and there is jolting and skidding, so you'll find that here steam engine drive, the coefficient of adhesion is low and the chances of slipping off the wheels from the train is high. So that is why you'll find that if you compare the steam engine drive with the electric traction, you'll find that when you're negotiating the turn, the steam engine drive, basically you have to reduce the speed when you're negotiating a turn. But that is not the case with the electric locomotive, because in that case the coefficient of adhesion is better, and when you're negotiating the turn, there's no need to reduce down the speed. You can the electric locomotive can negotiate the curve even at a higher speed without reducing the speed of the train. Thank you.